Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera to all students. We are still in DRM1413 manufacturing technology, which is in chapter 6. So today we are going to look at on new subtopics in chapter 4, which is advanced machining. So first of all, let's look at what are the content for today's topic. So first of all, we are going to look at on the introductions on advanced machining, and then we are going to look at on electrochemical machining, electric discharge machining, wire EDM, chemical machining, and several other processes under chemical machining. So conventional machining process like turning, drilling, milling, which use a sharp cutting tool to form a chip from a work by shear deformation. In addition to these conventional methods, there is a group of processes that use other mechanisms to remove material. The term non-traditional machining actually refers to this group that remove excess material by various techniques involving mechanical, thermal, electrical, or chemical energy. They do not use a sharp cutting tool in the conventional sense. The non-traditional process have been developed since World War II, largely in response to new unusual machining requirements that could not be satisfied by conventional methods. While these requirements and the resulting commercial and technological importance of non-traditional process include: number one, the need to machine newly developed metals and non-metals. These new materials often have special properties like high strength, high hardness, high toughness that make them difficult or impossible to machine by conventional methods. Number two, the needs for unusual or complex part geometries that cannot easily be accomplished, in some cases are impossible to achieve by conventional machining. Number three, the needs to avoid surface damage that often accompanies the stresses created by conventional machining. Many of these requirements are associated with aerospace and electronic industries, which have become increasingly important in recent decades. There are literally dozens of non-traditional machining processes, which most of which are unique in their range of applications. In the present topic, we will discuss those that are more important commercially only, like the one that have been mentioned in previous slide just now. So the non-traditional processes are often classified according to principal form of energy used to effect material removal. By this classification, there are four types exist. Number one, through mechanical energy in some form other than the action of a conventional cutting tool is used in these non-traditional processes. Erosion of the wood material by a high velocity stream of abrasives or fluid, or both, is the typical form of mechanical action in these processes. And number two is electrical. These non-traditional processes use electrochemical energy to remove material. And the mechanism is the reverse of electroplating. Number three, number three is a thermal. While these processes use thermal energy to cut or shape the work part, the thermal energy is generally applied to a very small portion of the work surface, causing the portion to be removed by fusion or by vaporization. The thermal energy is generated by the conversion of electrical energy. Number four is a chemical. Most materials are susceptible to chemical attack by certain acids or other agents. In chemical machining, chemicals selectively remove material from portions of the work part, whereas other portions of the work of the surface are protected by mask. So these are the example for non-conventional processes that exist in the market or in industry. like ECM, EDM, wire EDM, chemical machining, electro chemical grinding, laser beam machining, electron beam machining, water jet machining, abrasive water jet machining, abrasive jet machining, ultrasonic machining, and also deburring processes. So now let's look at the most common non-conventional process or advanced machining process that is being used in the market, which is electrochemical machining or ECM. So ECM is an important group of non-traditional processes use electrical energy to remove material. This group is identified by the term electrochemical processes because electrical energy is used in combination with chemical reactions to accomplish material removal. In effect, these processes are the reverse of electroplating. The work material must be a conductor in the electrochemical machining processes. The basic process in this group is electrochemical machining, which is ECM. Electrochemical machining removes metal from an electrical conductive workpiece by anodic dissolution, in which the shape of the workpiece is obtained by a formed electrode tool in close proximity to but separated from the work by a rapidly flowing electrolyte. The ECM is basically a deplating operation. As illustrated in the figure over here, the workpiece is the anode and the tool itself is the cathode. The principle underlying the process is that material is depleted from anode and deposited onto the cathode. The difference in ECM is that the electrolyte bath flows rapidly between the two poles to carry off the depleted material, so it does not become plated onto the tool. The electrode tool, usually made of copper, brass or stainless steel, is designed to possess approximately the inverse of the desired final shape of the part. An allowance in the tool size must be provided for the gap that exists between the tool and the work. To accomplish metal removal, the electrode is fed into the work at a rate equal to the rate of metal removal from the work. Metal removal rate is determined by Faraday's first law, which states that the amount of chemical change produced by an electric current is proportional to the quantity of electricity passed. And water is used. Water is used as the base for electrolyte in ECM to reduce electrolyte resistivity. Salts such as natrium chloride or natrium nitrite are added in solution. In addition to carrying off the material that has been removed from the workpiece, the flowing electrolyte also serves the function of removing heat and hydrogen bubbles created in the chemical reactions of the process. The removed work material is in the form of microscopic particles that must be separated from the electrolyte through centrifuge, sedimentation, or other means. The separated particles form a thick sludge whose disposal is an environmental problem associated with ECM. Large amount of electrical power are required to perform ECM. As the equation indicates, rate of metal removal is determined by electrical power, specifically the current density that can be supplied to the operation. The voltage in ECM is kept relatively low to minimize arcing across the gap. Electrochemical machining is generally used in application in which the work metal is hard or difficult to machine, or the work geometry is difficult to accomplish by conventional machining methods. work hardness makes no difference in ECM because the metal removal is not mechanical. Typical ECM applications include die sinking, which involves machining of irregular shapes and contours into forging dies, plastic molds, and other shaping tools. Number two, multiple drilling holes, in which many holes can be drilled simultaneously with ECM, and conventional drilling would probably require the holes to be made sequentially. Number holes that are not around because ECM does not use a rotating drill. And number four, deburring. Advantages of ECM include little surface damage to work part, no burrs as in conventional machining, low tool wear, and also relatively high material removal rate for hard and difficult to machine metal. Whereas the disadvantages of ECM include number one, significant cost of electrical power to drive the operation, and number two, problems of disposing of the electrolyte sludge. Other than that, these are the formula to do analysis for ECM process. Like for example, volume of metal removed, current, resistance, and also resistance, as well as feed rate FR over here. And the rest of the terms you can look at over here in this slide. So now let's look at an example for ECM. Let's read this example together. An ECM operation is to be used to cut a hole into a plate of aluminium. The thickness is equals to 12 mm. Specific removable rate of aluminum is given as follows. The hole has a rectangular cross section, which is 10 mm times 30 mm. Current is given, which is 1200 ampere. Efficiency is given, which is equals to 95%. And the question asks us to find feed rate and time required to cut through the plate. So the feed rate can use this formula as well as time required. Sorry. So first thing is, we know that the frontal area of electrode is given, which is A equals to 10 times 30. So equals to 200 mm square. And we just substitute into this formula for feed rate. C is given just now. Ampere current is given. So substitute everything, you should be able to get the value of feed rate, which is equals to 0.1376 mm per second. And since the efficiency is given by 95%, so times with 95%, then we should be able to get the feed rate at that efficiency is equals to 0.1307 mm per second. Whereas for time to machine, for through 12 mm plate, use this formula. And I think just substitute the information and use feed rate from this value, I mean the one that you have calculated just now, then you should be able to get the time to machine, which is equals 1.53 minutes. Now let's move on to second types of advanced machining process, which is electric discharge machining EDM. While electric discharge machining EDM is one of the most widely used non-traditional processes, an EDM setup is illustrated in figure A over here. The shape of the finished work surface is produced by a formed electrode tool. The sparks occur across a small gap between tool and work surface. The EDM process must take place in the presence of a dielectric fluid, which creates a path for each discharge as the fluid becomes ionized in the gap. The discharges are generated by a pulsating direct current power supply connected to work and the tool. Whereas figure B shows a close view of the gap between the tool and the work. The discharge occurs at the location where the two surfaces are closest. Um, the dielectric fluid ionizes at this location to create a path for the discharge. The region in which a discharge occurs is heated at extremely high temperature, um, so that a small portion of the work surface is suddenly melted and removed. The flowing dielectric then flushes away small particles because the surface of the work at the location of the previous discharge is now separated from the tool by a greater distance. This location is less likely to be the site of another spark until the surrounding regions have been reduced to the same level or below. Although the individual discharges remove metal at a very localized point, they occur hundreds or thousands of times per second, so that a gradual erosion of the entire surface occurs in the area of the gap. Two important process parameters in EDM are discharge current and frequency of discharges. As either of these parameters is increased, metal removal rate also will keep increasing. Surface roughness is also affected by current and frequency, as shown in graph A here. So the best surface finish is obtained in EDM by operating at high frequencies and low discharge currents. As the electrode tool penetrates into the work, overcutting occurs. Overcut in EDM is the distance by which the machine cavity in the work part exceeds the size of the tool on each side of tools, as illustrated in figure A. It is produced because the electrical discharge occurs at the sides of the tool as well as its frontal area. Overcut is a function of current and frequency, as can be seen in figure B, and can amount to several hundreds of millimeters. The high spark temperatures that mark the work also melt the tools, creating a small cavity in the surface opposite the cavity produced in the work. The tool wear is usually measured as the ratio of work material removed to tool material removed. This wear ratio ranges between 1 to 100 or slightly above, depending on the combination of work and electrode material. Electrodes are made of graphite, okay. Electrodes are made of graphite, copper, brass, copper tungsten, silver tungsten, and other materials. The selection depends on the types of power supply circuit available on EDM machine, the type of work material that is to be machined, or whether roughing or finishing is to be done. Graphite is preferred for many applications because of its melting characteristics. In fact, graphite does not melt. It vaporizes at very high temperatures, and the cavity created by the spark is generally smaller than for most other EDM electrode materials. Consequently, a high ratio of work material removed to tool wear is usually obtained with graphite tools. And the hardness and strength of work material are not factors in EDM because the process is not a contest of hardness between tool and work. The melting point of the work material is an important property. Dielectric fluids used in EDM include hydrocarbon oils, kerosene, or distilled or deionized water. The dielectric fluid serves as insulator in the gap except when ionization occurs in the presence of spark. Its other functions are to flush debris out of the gap and remove heat from tool and work part. Applications of electric discharge machining includes both tool fabrication and parts production. The tool for many of mechanical processes discussed in this topic are often made by ADM, including molds for plastic injection molding, extrusion dies, wire drawing dies, forging and heating dies, and sheet metal stamping dies. As in ECM, the term die sinking is used for operation in which a mold cavity is produced, and the EDM process itself is sometimes refers to as RAM EDM. For many of the applications, the materials used to fabricate the tooling are difficult to machine by conventional methods. Certain production parts also call for applications of ATM. Example like delicate parts that are not rigid enough to withstand conventional cutting forces. Hole drilling, where the axis of the hole is at an acute angle to the surface so that the conventional drill would be able to start the hole, and also production machining of hard and exotic metals. Now, let's look at another types of advanced machining, which is wire EDM. Electric discharge wire cutting, EDWC, commonly called as wire EDM. It is a special form of electric discharge machining that uses a small diameter wire as the electrode to cut a narrow curve in the work. The cutting action in wire EDM is achieved by thermal energy from electric discharges between the electrode and the workpiece. The wire EDM is illustrated in figure here. The workpiece is fed past wire to achieve the desired cutting path, somewhat in the manner of a bandsaw operation. Numerical control is used to control the work part motions during cutting. As it cuts, the wire is slowly and continuously advanced between a supply spool and take-up spool to present a fresh electrode of constant diameter to the work. This helps to maintain a constant curve width during cutting. As in EDM, wire EDM must be carried out in the presence of dielectric. This is applied by nozzle directed to the tool work interfaces as in our figure here, or the work part is submerged in a dielectric pot. Wire diameter normally ranges from 0.076 to 0.3 mm depending on required curve die width. Materials used for the wire include brass, copper, tungsten, and molybdenum. Dielectric fluids include deionized water or oil. As in EDM, an overcut exists in wire EDM that makes the curve larger than the wire diameter. These overcuts normally in the range of 0.02 until 0.05 mm. Once cutting conditions has been established for a given cut, the overcut remains fairly constant and predictable. Although wire EDM seems similar to bandsaw operations, its precision far exceeds that of bandsaw. The curve is much narrower. Corners can be made much sharper. The cutting forces against the work are nil. In addition, hardness and toughness of the work material do not affect cutting performance. The only requirement is that the work material must be electrically conductive. The special features of wire ATM make it ideal for making component for stamping die. So let's move on to next advanced machining process, which is chemical machining. Well, chemical machining is also a non-traditional process in which material is removed by means of a strong chemical action. Applications as an industrial process began shortly after World War II in the aircraft industry. The use of chemicals to remove unwanted material from a work part can be accomplished in several ways, and different terms have been developed to distinguish the applications. The terms include chemical milling, chemical blanking, chemical engraving, photochemical machining. What else? Chemical engraving and photochemical machining. They all use the same mechanism of material removal, and it is appropriate to discuss the general characteristic of chemical machining before defining individual processes just now. The chemical machining process consists of several steps. Um, Differences in applications and the way in which the steps are implemented account for different forms of CHM. The steps are includes number one, cleaning. Cleaning. The first step is cleaning operations to ensure that material will be removed uniformly from the surfaces to be etched. Number two, masking. A protective coating called a masking is applied to certain portion of the part surface. This masking is made of material that is chemically resistant to etching. It is therefore applied to those portions of the work surface that are not to be etched. Number three, etching. And this is the material removal step. The part is immersed in an agent that chemically attacks those portions of the part surface that are not masked. The usual method of attack is to convert the work material into a salt that dissolves in the agent and is thereby removed from the surface. When the desired amount of material has been removed, a part is withdrawn from the agent and washed to stop the process. Number four is demasking. The mask is removed from the part. Well, the two steps in chemical machining that involve significant variations in method, material, and process parameters are masking and etching, which is step 2 and step 3. Masking materials include neoprene, polyvinyl chloride, polyethylene, and other polymer. Masking can be accomplished by any of three methods like cut and peeling. Number 2, photographic resist. Number 3, screen resist. The cut and peel method applies the masking over the entire part by dipping, painting, or spraying. After the masking has hardened, it is cut using a scribing knife and peeled away in the areas of the work surface that are to be etched. The masking cutting operation is performed by hand, usually guiding the knife with a template. The cut and peel method is generally used for large work part, low production quantities, and where accuracy is not a critical factor. As the name suggests, the photographic resist method uses photographic techniques to perform the masking step. The masking materials contain photosensitive chemicals. They are applied to the work surface and exposed to light through a negative image of the desired areas to be etched. These areas of the masking can then be removed from the surface photographic developing technique. This procedure leaves the desired surfaces of the part protected by the masking and the remaining areas unprotected, vulnerable to chemical etching. Photoresist masking techniques are normally applied where small parts are produced in high quantities and close tolerances are required. The screen the screen resist method applies the masking by means of silk screening methods. In this method, the masking is painted onto the surface through a silk or stainless steel mesh. Embedded in the mesh is a stencil that protects those areas to be etched from being painted. The masking is those painted onto the work areas that are not to be etched. The screen resist method is generally used in applications applications that are between the other two masking methods in terms of accuracy, part size, and production quantities. Selection of etchant depends on work material to be etched, desired depth and rate of material removal, as well as surface finish requirements. The etchant must also be matched with the types of masking that is used to ensure that the masking material is not chemically attacked by the etchant. So whereas for chemical milling, chemical milling is was the first CHM process to be commercialized. During World War II, an aircraft company in the United States began to use chemical milling to remove metal from aircraft components. They referred to their process as the term chem mill process. Chem mill process. Well, today chemical milling is still used largely in aircraft industry to remove material from aircraft wing and fuselage panels for weight reduction. It is applicable to large parts where substantial amounts of metal are removed during the process. The cut and peel masking methods is employed. A template is generally used that takes into account the undercut that will result during etching. And the sequence of process steps is illustrated in the figure here. Okay, in this figure now, all chemical milling produces a surface finish that varies with different work material. As depth increases, finish become worse, approaching the upper side of the ranges given with certain ranges of a depth. And metallurgical damage from chemical milling is very small, perhaps around 0.005 mm to the work surface. Okay, so now let's look at for chemical blanking. Chemical blanking uses chemical erosion to cut very thin sheet metal parts. In both instances, conventional punch and dry methods do not work because the stamping forces damage the sheet metal, or the tooling cost would be prohibited. Chemical blanking procedures part that are burr-free and advantage over conventional shearing operations. Methods used for applying the masking in chemical blanking are either the photoresist method or the screen resist method. For small and or intricate cutting patterns and close tolerances, the photoresist method is used. Screen resist masking methods are not nearly so accurate as photoresist. The small work size in chemical blanking excludes the cut and peel masking method. Using the screen resist method to illustrate steps in chemical blanking as shown in this figure over here. Because chemical etching takes place on both sides of the part in chemical blanking, it is important that the masking procedure provides accurate registration between the two sides. Otherwise, the erosion into the part from opposite directions will not line up. This is especially critical with small part sizes and intricate patterns. Application of chemical blanking is generally limited to thin materials or intricate patterns for reasons given in the preceding. Maximum stock thickness is around 0.75 mm. Also, hardened and brittle materials can be processed by chemical blanking, where mechanical methods would surely fracture the work. And last but not least is photochemical machining under CHM. Photochemical machining is chemical machining in which the photoresist method of masking is used. The terms can therefore be applied correctly to chemical blanking and a chemical engraving, where these methods use photographic resist method. PECM is employed in metalworking when close tolerances and or intricate patterns are required on flat parts. Photochemical processes are also used used extensively in electronics industry to produce intricate circuit design on semiconductor wafers. As can be seen in figure here, it shows that the sequence of steps in photochemical machining as it is applied to chemical blanking. There are various ways to photographically expose the desired image onto the resist. The figure shows the negative in contact with the surface of the resist during exposure. This is contact printing, but other photographic printing methods are also available that expose the negative through a lens system to enlarge or to reduce. So that's all for today's lecture, and therefore this is the end of chapter 4. So in the next lecture, we are going to look at on our new topic, which is chapter 7. As for the conclusion, these are the exercises which you can do for this chapter, and you don't have to submit at the end of this lecture, but you can gather all together all the exercises that have been given to you and submit at the end of this semester. With that, I thank you very much for your kind attention and time, and see you again in the next class. Okay, thank you and bye.